In the previous section, we have covered the different analog pulse modulation techniques. PAM, pulse amplitude modulation, pulse width modulation, PWM, and pulse position modulation, PPM. So, in this section, we will start with digital modulation, digital pulse modulation techniques. So, the first one we are going to discuss over here is pulse code modulation, PCM, pulse code modulation. So, this is the practical block diagram for a PCM or a pulse code modulation or a PCM generator. So now I'll explain what are the blocks in a PCM transmitter. So the first block over here is a low pass filter with a cutoff frequency FM. You know what is a low pass filter? It will pass all the frequency till the cutoff frequency. Above cutoff frequency it will not pass. So XT, that is our message signal. Anyway, this is a digital pulse modulation technique. So digital pulse means your message should be in digital. And this XT, this message signal is a continuous time signal. As I told you earlier, all the signals available in our nature, in the real world, are analog in nature, continuous time in nature. So if you want to deal with the digital, we have to convert it to digital signal. So this analog signal, this continuous time message signal first should convert it to discrete form. So for that we have to do the sampling process. So if you want to properly reconstruct, sufficient number of samples should be taken. So we discussed about sampling theorem before. So the number of samples should be greater than or equal to 2 times FM. Then only we will be able to reconstruct. So we have to ensure that the frequency of message signal to be FM. The message signal may contain different frequency components. So what you have to do is, first we have to band limit our message signal so that the highest frequency of your message signal should be equal to FM. Highest frequency of the message signal should be equal to FM. No other frequency above FM should be there. So that is the reason this low pass filter being used here. You are band limiting your message signal to a frequency FM, maximum frequency FM, so that you can sample at the rate 2 FM, because you should know what is the maximum frequency. So that is the function of your low pass filter. So by your low pass filter, your signal XT is band limited to FM Hertz frequency. Now we'll move to the next block, and the output of your first block is band limit, say for example like this is your XT. Now it's band limited to a maximum frequency of FM. This is the maximum frequency of your signal. So now in this is a sample and hold circuit. It samples the signals at the rate Fs, where Fs should be greater than or equal to 2 FM. So there is a timer control is providing from here, so that the sample and hold circuit should work in such a way that your Fs should be greater than or equal to 2 FM. So the output of the sample and hold circuit is represented as XNTS. It is just like a palm signal, because this is your original signal. This one is your XT. This is your original signal. So now what I'm going to do, I'm going to sample it. So it is something like this. It was a sinusoidal shape. So we are getting something like this. So now how many, each instant, this was the time axis. Now this is the first, this X and TS. So each one I am sampling at TS interval. TS, this second sample will come as 2S, third sample will come as 3TS, 4TS, 5TS, 6TS, like that. Now each sampling instant. So this one is x1 TS, this will be x2 TS, this will corresponds to x3 TS, like that. This is like xn TS. Now we are telling in terms of samples. So it is a palm signal. So this is the output of sample and hold circuit. Now the next is a Q level quantizer. The Q level quantizer, it will compare your XNTS with a fixed value. This will be more clear when I am explaining this pulse code modulation to you. After explaining this again, I will come back to block diagram. So here XQNTS, so that is the output of Q level quantizer. So each XNDS will be compared against a fixed digital level, and then which digital level this XNDS is nearby, it assigns to that level. So it is not exactly XNDS, it will assign to the nearest quantized value. So that output is called XQNTS. So there will be a difference between quantized output and your actual XNTS. That is called quantization error. So now we will apply quantizer level in such a way that the quantization or error should be minimum. So this output is called XQNTS. Now this XQNTS now given to a binary encoder. So it will encode whatever this value corresponding binary bits, it will encode. So this data is now converted to digital. Now after encoding this binary encoder, maybe a 3-bit or a 2-bit or a 4-bit binary encoder corresponding to each sample. So then we cannot convert like 3-bit or 4-bit as such. So again what we will use, a parallel to serial converter will take, and then the data will be converted. Each 4-bit data as a serial wise we will transmit at the PCM output. So this is the block diagram of a practical block diagram of a PCM generator.